Hello again. In this session, we will talk about the force tension. Now, tension is the force that comes into play whenever there is a change in length of an object. Now, most often we would see this force whenever we have a string or a spring. So let's first talk about strings. Now, in physics, whenever you would see two things connected through a string or a thread, we would work under certain assumptions unless specified otherwise. So we are always working under two assumptions, the first of which is that strings are inextensible. That is, their length cannot change. Right. And the second assumption that we work on is that strings are massless. So, whenever you see a string attached between two blocks or any two objects, you can directly assume that that string is inextensible and it has zero mass. Right. So now, say you have a string using which you are pulling a block. Let's say this block has a mass m. So if a force F is applied, then what would happen? You know that the block will start to move. But in this case, the point of application of force is far away from this block. So this force is transmitted through the string. And how does it get transmitted? Once you apply this force, this string has a tendency to get extended. So the entire string comes under tension. And this tension is transmitted to the other end, and hence that force F which you have applied at this end is applied at the block M. Right. So, let's see a few properties of this force tension. The first property is that tension is always a pulling force. Now, it is fairly obvious that you can never push a block using a string. Consider the same situation. Instead of this force F being leftwards, if it was rightwards, you would not see the block moving. Instead, the string would simply slack. Right? So, tension is always a pulling force. And remember that it pulls both its ends. For example, let's take a situation where you have two blocks connected by a string, and then say you're pulling the block at the right. Let's call them A and B. So if you start pulling block B, this thread which is connecting these two will come under tension and will start pulling. Now, this thread will not only pull A, it will also pull B. Right? So as soon as this string or this thread comes under tension, it starts to pull at both its ends. So it will pull this end towards the center, and it will at the same time also pull from the other end towards the center. So basically, once a string or a thread is under tension, it will try to pull both its ends inwards. Right? So tension is always a pulling force, and it pulls at both its ends. So we can also write this, that it pulls both ends. You can think of a rubber band to remember this. When you stretch that band, you see that both its ends are pulled towards the center. Right? And secondly, this force always acts along the length of the string. So it will always act along the length of the string or a spring. We will discuss spring later, but it applies to both. So this tension force will always act along the length of the spring or the string in whichever we are seeing that tension. Right. So what this means is that if you have a situation like this, say you're pulling a block where the thread actually bends after some point. So when you pull this block, this tension which acts on this block will act along this length. It's fairly obvious, right? So these are the two properties of this force tension. It is always a pulling force and it always acts along the length of the string. So let's take a fairly simple example and apply what we have just learned. So let's say there is a block of mass 10 kg. On this block we are applying a force of 50 Newton at an angle of, let's say, 30 degree with the horizontal. Right. So we wish to find the acceleration of this block. Now, to do this problem, we will repeat the steps that we learned in the last session. First of all, we will identify our system. In this case, we don't have a lot of choices, right? So we will take the 10 kg block as our system. So this is our system. Now, next comes drawing the free body diagram, where we will not draw the surfaces, we will draw this block as a point and then list down all the forces which are acting on this block. Right. So the first force which we see is clearly the 50 Newton force. So this is the 50 Newton force acting at 30 degrees with the horizontal. Next comes the weight of this block. The weight of this block we know will be mass times the acceleration due to gravity. Since the mass is 10, you multiply this with the acceleration due to gravity, which is 10 again, you get that its weight is 100 Newton. So you have 100 Newtons acting downwards. Then we know that this block is in contact with ground, and hence the ground will offer some normal reaction, and this normal reaction will act vertically upwards. So we are denoting this by N. So here on we will avoid writing this N to symbolize Newton because it gets confusing with normal reaction, right? So now once we have this FBD, the next thing to do that we did not have to do in the earlier cases is that whenever you see a force which is not aligned with the axis, you break that force down into two components, one purely along X, the other purely along Y. Now we have discussed this a few times about breaking a vector, and we do that every time we see a vector which is not aligned with the coordinate axis that we have taken. In this case, the obvious choice for coordinate axis was horizontal and the vertical direction, because the other two forces are purely vertical. Right. So let me draw this on the side, that this is the x-axis, this is the y-axis. So you have 100 Newtons acting downwards, and then you have a normal reaction which is vertical. This force of 50 Newton acts at 30 degrees with the horizontal. So we will break this down into two components. Now you know that the component, that the axis between which the angle is enclosed, gets the cos component. If you have any confusion about it, you can complete the triangle as we had discussed earlier and then see whether you should have cos theta or sin theta. Right. So in this case you will have 50 cos theta, 50 cos 30 degrees in the horizontal direction, and in the vertical direction you will have 50 sin 30 degrees. Let me just repeat this once. We are getting a cos component here because the angle is with the x-axis. So whichever axis the angle is made with, you will see a cos component on that side. Right. So once we have done this, let's calculate the values of this. Sin 30, I hope you are aware, is half. So this becomes 25, and cos 30 is root 3 by 2. So we basically have 25 times 1.7. So if we multiply them, you have 42.5 newtons, right? So the single force of 50 newton can be broken down into two components, the horizontal component being 42.5. So this side you have a force of 42.5, and in the vertical direction the force has a magnitude of 25 newtons. So the single 15 newton force has been broken down into two simpler forces. So the revised free body diagram looks something like this. You have 25 newtons upwards, then you have another normal reaction upwards, then a force of 42.5 newtons which is horizontal, and once again a vertical force of 100 newton. Right. So now, so far we have identified our system, we have drawn a free body diagram, we broke down the force which was not aligned with the coordinate axis, and now we have a simplified free body diagram where all the forces are aligned with the axis. Here on, the analysis is once again very simple. You have to look at the forces along the x and the y direction separately. So first of all, let's talk about the forces which are along the y direction. Now y direction is simple because we can see that the block will not move in this direction, right? So we can say that n plus 25 is equal to 100 newton, and hence n is equal to 75, right? We balanced the forces because acceleration was 0. So basically the equation is that the net force is 0, and we applied that by using the fact that for the net force to be 0, the upward force must balance the downward force, right? For the horizontal, we'll once again write the second law of motion, that is F equal to ma. So 42.5 is equal to the mass, which is 10 kg, into acceleration. So we get the value of acceleration as 4.25 meter per second square. So this is the value of acceleration. So let's once again go over the procedure. We had a 10 kg block lying on the ground with a 50 newton force acting on it with 30 degrees with the horizontal, right? So first of all, we identified the system, which was fairly simple as there's only one choice. Once we had the system, we drew the free body diagram. In the free body diagram, we saw that one of the force was not aligned with the coordinate axis, so we broke it down into components. Once we got the simplified components, we once again separately wrote equations for x and y and solved them. Now, in this case, I directly stated that this block will not move. Now, you could check whether or not the block will move. How do we do that? If this normal reaction had turned out to be negative, if this force, just hypothetically, if this was 125, the normal reaction would have been minus 25. Normal reaction can never be negative. This is because a negative value would imply it is acting in the opposite direction. But normal can only act in one direction, which is the direction in which it can push, right? So if at all we were getting a negative normal implies that your assumption is wrong. So whenever you're solving a problem and you have to make certain assumptions, if you get a negative normal, you should know that the assumption that you've made is wrong, right? Also, why we could directly say that this block would not lift is that the normal acts only if it is needed, right? So in this case, there was a 100 Newton force which acted downwards, and there was only a 25 Newton force acting upwards. So there was clearly a deficit of 75 Newton, for which the ground had to apply some normal reaction. Right. So this summarizes all that we had in this problem. Let me write the steps once again. You first identify the system, then you draw the free body diagram. We have done this so far. The third thing that we saw this time is break the forces not aligned with the axis. So you break down the forces which are not aligned with the axis. And once you do that, you have a simplified free body diagram, after which you write equations for x and y separately. And when I say write equations, I basically mean apply the second law of motion. Right. So these are the 4 steps that we always repeat whenever we are analyzing forces. Right. So now that we understand strings, let's briefly look at how springs behave. Now, the one major difference between a string and a spring is that strings can only pull, but springs on the other hand can push when they are compressed. Right. So let's first look how a spring exerts force. So we will show a spring by the symbol that I have drawn. So this represents a spring. Now, you know that whenever you alter the length of a spring, it will offer some force. So let's say I pull it outwards by an amount x. Then it was experimentally found that the restoring force that the spring applies, the restoring force being the force with which it pulls its end inwards, is proportional to this change in length. Now we have discussed that whenever we have a proportionality sign, then to remove a proportionality we need to replace with a constant to turn this into an equality. Similarly, in this case we will use a constant, and this constant K is called spring constant. And this spring constant depends on the material that you are using and the geometry of the spring, that is how tightly or loosely that spring is bound. Right. But for a given spring, for any given spring that you take, the spring constant will remain the same. Right. So the force it offers, a spring offers, is equal to K times X. And this X could either be compression or elongation. So if instead of elongating, had you compressed it by an amount X, the force it would have offered would have the magnitude Kx, and it would be outwards. Right. Now, to be very correct, this force is given by the expression F equal to minus Kx. The minus sign implying that if you stretch it by X, if you move the spring outwards, it will exert a force towards the right. Right? So if you pull it outwards, the force is inwards, and if you push it inwards, the force is outwards. So this minus sign implies that whichever direction in which X is, the force acts in the direction opposite to that. Right. So in case of spring, if you change the length by amount X, the force offered is equal to K into X, where K is called the spring constant of that spring. So let's take a simple example. Let's say you have a spring with a spring constant of 50 Newton per meter. So notice that the units for spring constant are Newton per meter. It is very simple to derive. You see that F is equal to K into X. So K is basically F by M. Force is measured in Newton and it is F by X, and X is measured in meters. So the units become Newton per meter. Right. So this spring, which has a spring constant of 50 Newton per meter, has a block attached to it which has a mass of 5 kg. So we move this block inwards by 10 centimeters and then release this block. You have to find the acceleration of this block right after the block is released. So let me repeat the problem. We have a spring of spring constant 50 Newton per meter, a block of 5 kg attached to it, and we have compressed the spring by 10 centimeters, and we have to find the acceleration right after the block is released. Right. So to find the acceleration, we obviously need to find the force which is acting on this block, because we already know its mass. So the second equation of motion is F equal to M into A. In this equation, M is known and F can be found out, since for this spring we know the spring constant as well as the compression in the spring. So the force offered by the spring we have seen is K into X. K we know is 50 into X. Now please pay attention that when you're substituting value of X, it must be in the standard units, the SI units, and SI unit for length is meters. So we'll have to convert centimeters into meters. I hope you know that to do so we'll have to divide this value by 100, because on dividing a value in centimeters by 100 we get the corresponding value in meters. So the value in meters becomes 0.1 and hence the force is 5 Newton. So we have a 5 Newton force acting on a 5 kg block, and hence obviously the acceleration would be 1 meter per second square. Right. So this was all about tension. In the next session we will learn about frictional force. Thank you.